So you did the tables, you got the frequency distributions and stuff like that. Did you have any questions on making those?
I don't really think so. I don't know. It's like we're still just we learned it yesterday. We're applying it today. So.
Okay. There's two different types of data. There's categorical.
Yeah. I can't see your screen.
All right, still not showing. Let me try her again. There, it should be coming through. There's categorical, sometimes called qualitative. And then there is numerical, or sometimes called quantitative, depending on what textbook you're looking at. And so categorical, all of statistics is about asking a question, what's your favorite color? What's your major? How tall are you? How much do you weigh? What's your income? If the answer to that question is a category, that would be a categorical data. If the answer to the question is a number, your numerical data. So if it's your favorite color, it's pretty simple. You're going to list your color here, your frequency, and all the colors that were given. And then there, whatever the frequency is. Like that. For numerical data, it can be a little bit more difficult. There is grouped and ungrouped data. You have discrete numerical data. For discrete numerical data, that is basically counting. Like how many classes are you taking? How many cars do you own? How many children do you have? Those are things that are counted. And then there's continuous, which are things that are measured, which is your height, your weight, or whatever. And the thing with continuous and being measured is no matter how close in value two numbers are, you can always find a value that's in between them. So if you have, two people, one is 5'10" and 5/8, and the other one is 5'10" and 11/16, it's still possible for a value to fall in between them in continuous data. Continuous data must be grouped for a frequency table. Discrete data can be grouped or ungrouped. Okay, so for example, let's say we're asking number of classes that you're taking right now. Well, there's not going to be too many students that are going to be taking more than like 6 or 7 classes at a time. So we could just list them all out. If they're taking 0 classes, they're not a student. Let's say the most that anybody had was 6. So we could list them all out individually and then put whatever the frequencies are in here. If you're asked, I'm trying to think of a discrete one, a counting one that would be multiple. I don't know, you take a bag of M&Ms and ask how many M&Ms are in that bag. That's still counting, it's still discrete. But there's probably going to be a wide variety. So most likely it's not 0, and hopefully maybe none of them have less than 10. So you might go 10 to 14, 15 to 19, 20 to 24, and so on, and put them in those frequencies. For continuous data where it's measured, it's always going to have to be grouped like that. For example, let's say we're measuring height. And let's say our shortest person is 60 1/2 inch. Our tallest is 74 3/4 inches. We have to come up now with groups that will get from the smallest up to the largest. And how many groups we're going to use depends on how many people are there. If we only measured 10 people, we probably don't want more than 2 or 3 groups, because otherwise each group's only going to have 1 or 2 people in it. If we measured 100 people, we might want 5 or 6 groups or maybe more so that they're divided up. The toughest part about dealing with grouped numbers in the frequency table is figuring out what those groups should be. Because the groups all have to be the same size. Notice these are all, the width of 4. If you take 14 minus 10, you got 4. 19 minus 15, you got 4. They're all the same size. Well, same here. They have to be all the same size, but we don't want to start too far below the smallest one, and we don't want to go too far above the top one either. We want the data to be kind of equally spread out within them. So let's say I'm going to go from 60 to 75 here. Now, like I said, if we have like 100 people here, we don't want to put this in just 3 groups because that would not adequately cover. We'd have like 30 in a group, and it wouldn't give us a nice picture of how they're divided up. But for this purpose, let's say that we have, about 30 people. So dividing them into 5 groups is going to work out really well. So here we've got a range. I don't know if we've talked about range yet. The range of 75 minus 60 is 15. If you divide that by 5, that's going to be a group width of 3 per group. Now, I don't want to go 60 to 63. I want the next group to start at 63. So I go 60, 63, 66, 69, 72. Now, depending on how precisely we're measuring, let's say we're going down to the nearest 100th of an inch when we're measuring this height. This has to go to 100th of an inch less than where this one starts. So that'd be 62.99. If we're only measuring to the nearest 10th of an inch, we'd only have to go to 62.9. So we have to make sure that there isn't room, based on the precision of our measurement, there isn't room for somebody to fall in between classes. So I think you get the picture there. They said that is the toughest part, is getting good at picking the size of those groups and how many of those groups you're going to have. Some textbooks go through, it's, n is the number of items in the whole set, and it's the square root of n, whatever, to give you how many groups you need. I'm not sure how your textbook is handling that, but we'll just leave it at that you have to make sure there's no room in between those classes and that they're all the same size. So now, have you talked about distributions at all? Other than the frequency table?
Where you divide it up, where you divide your ranges. You multiply by how many you have.
Oh yeah, trying to do a mean or standard deviation within a frequency table?
Yeah.
Okay. What that's all describing is the distribution itself. What the distribution is all the data values in the set and how they fall. For example, let's say I want to take the historic grades of students in one of my classes. Let's say they range from 60 to 100 in the class. So I'm going to make a number line that covers that whole range of all the possible outcomes. And I'm going to say, let's say a student has a 92, I'm going to put a dot above, or an 82, I'll put a dot above 82. Another one has a 77, I'll put a dot above 77. A 91, maybe a 69, an 81, another 82. So if there's a second person, I put a dot above it. And as you keep putting those students, those numbers on the distribution, what happens is they start building up. And they're going to form a shape that tells us how this data is laid out. And as that builds, generally it'll form a shape something like this, which is called the normal distribution. And most of us have heard it referred to as the bell curve. The reason it's called a normal distribution is in nature, that is the shape that most sets of data normally will take on. That's the normal shape of data. So when we're talking about measures of center and spread, what we're talking about is where is the center of this curve. Here it looks like the center of that curve is about 78 or so. The spread is its width across there. So let's say I have another curve that looks like this, and it's sitting right here. Well, the difference between the black curve and the green curve, they have the same spread, but the center has changed. The green one has a higher center, a larger center. If I have a curve like this, now the black curve and the blue curve have the same center, but the blue curve is narrower. It has less spread. So all the calculations we do are in an effort to describe that center and spread. So for center, you have the mean, the median, and the mode. Have we gone over those yet? Okay. I'm not going to go over the calculations because they're pretty simple, unless you have any questions on any of them. Okay. Spread, you have the range. Sometimes the spread is called dispersion too, depending on what textbook you're talking about or you're dealing with. You have the range, which is what we did. That's just the largest, the maximum minus the minimum. And then you have standard deviation. Very closely related to standard deviation is something called the variance. They're really the same question. The standard deviation is just taking it one step further. Now, depending on whether you're doing the standard deviation of a population or a sample, it's slightly different. For a population, the symbol for standard deviation is the Greek letter sigma. It's the small letter sigma. And it is the square root of the sum of each x value, each value in the set, minus the mean. The symbol for the mean is x with a bar over the top of it. Actually, I gotta be careful. For a population, the mean is actually the Greek letter mu. So that equals a population mean. We're going to subtract each of those and square them, add them up. That's what the summation symbol is there for. And then divide by n, the number of items in the population. Actually use capital N for population. If it's a sample, S is used to represent the standard deviation. And it's calculated. It's going to look very much similar. It's x minus x bar is the symbol for a sample mean. And in a sample, we divide by the sample size minus 1. Because it isn't the whole population, we have a decreased level of degrees of freedom. And it's kind of a complex explanation as to why this is n minus 1 instead of n like it is for the population. But it's because we're not looking at everything. There's less room to vary. To calculate one of these, either one of these formulas is pretty much the same. All it's going to change is one step here. So it's a 6-step process to get the standard deviation. I'm going to take just a simple set of numbers here, like 5, 8, 11, 12, and 14 are going to be my numbers. Step 1 is to find the mean. So if I add those numbers up and find the mean, 5 and 8 is 13, plus 11 is 24, plus 12 is 36, plus 4 is 40. Divided by 5 gives me a mean of 8. Does that look right? That doesn't look right. 5, 13, 24, 36, 40. I did something wrong there.
No, it is 40.
It is 40, and dividing by 5 does give me a mean of 8. Oh, I got to put 14 here. That should be 50. So divided by 5 gives me a mean of 10. So that's step 1. Step 2 is we're going to subtract each number from the mean. Or subtract the mean from each number, I should say. So we've got 5, 8, 11, 12, 14. We're going to subtract our mean of 10 from each of those. So 5 minus 10 is negative 5. 8 minus 10 is negative 2. I'm going to fly through this a little bit. 11 minus 10 is 1. 12 minus 10 is 2. 14 minus 10 is 4. Step 3 is going to be to square each of those. So negative 5 squared. Be careful on your calculator. If you don't put parentheses around a negative when you square it, it'll try to give you a negative answer. Anything squared has to be positive. Negative 2 squared is 4. 1 squared is 1. 2 squared is 4. 4 squared is 16. Step 4, we find the total, the sum. So we add those all up. We've got what there? 20, 24, looks like a 49. So that was step 4. Step 5 is where it might be different. If it's a population, you divide by n. If it is a sample, you divide by n minus 1. So we're going to assume this is a sample. And so since the sample size is 5, 5 minus 1 would be 4. So we're going to divide by 4 here, which will give us 12.25. This number right here is what would be called the variance. To find the standard deviation, we have to go one step further. Step 6, which is the square root. Square root of 12.25, I believe, is 3.5. That's the standard deviation. Now, there is a shortcut formula for this. And if you're using large data sets, it's an easier way to do it. The standard deviation is the sum of the x squareds plus the sum of the x's squared, not plus, minus the sum of the x's squared, divided by n or n minus 1. I'm going to put in n minus 1 because I'm assuming it's a sample here. So our values were 5, 8, 11, 12, and 14. 5, 8, 11, 12, and 14. The sum there is 50. If we add those up. Put back here. If we square each of those, that's 25, 64, 121, 144, 196. What if we would add those up? What do we get? I'm going to just punch them in. We have a sum of 550. $50 squared is 2,500. So we have up here, that ain't going to work out, is it? This sample size may have been too small. Now anyway, I'll double check on that for you and I'll send it out. When I send out an email with the recording, I'll send that out for you. I don't use that shortcut formula very much anymore because the statistics classes I teach, we use the TI-84 calculator, this thing. That's why I've got one on my screen. Or we use Excel if it's more than 5 or 6 numbers. If you're using a set of, like you said, up to 50 numbers, you're going to want to use that shortcut formula. So I'll make sure on that shortcut formula and send it out for you. Okay, are you thinking you guys need to meet any more this semester, or do you think this is it?
One for the semester will probably involve time.
You've only got 1 week from today, is it? So.
I don't think Friday would hurt. You think? Think you could do Friday? Yeah, we probably do that, I suppose.
Okay.
Do it one last one for Friday.
Sounds good. I'll let them know to schedule for Friday.
All right, thank you.
You bet.